Two identically charged objects in a vacuum repel. To understand why, we must look past the macroscopic surface and dive into the subatomic space. At this scale, the interactions of individual point charges dictate the structure of all physical matter. The forces holding atoms together, the tension in a solid, and the chemical bonds of biology are entirely electrostatic in nature. For centuries, the understanding of this phenomenon was purely qualitative. Knowing that opposite charges attract and like charges repel is a useful observation, but it is entirely insufficient for mapping the complex, three-dimensional fields that govern molecular structures. To accurately predict how matter will behave under electrical stress, physics requires a precise quantitative formulation, a mathematical model that scales predictably from a single pair of electrons up to massive, continuous charge distributions. In the late 18th century, the French physicist Charles-Augustin de Coulomb set out to derive exactly that model. His objective was to isolate and measure the precise magnitude of the electric force acting between charged bodies. To understand how he succeeded, we will reconstruct Coulomb's physical experiment, formalize his findings into three-dimensional vector space, and ultimately test his law against the baseline cosmic force of gravity. This is the torsion balance, the sensitive instrument Coulomb used to measure incredibly faint repulsive forces. By observing the degree of twist in the suspended wire, he could calculate the physical force pushing two charged metallic spheres apart. But to establish a reliable mathematical law, Coulomb needed to know the exact amount of charge on each sphere. At the time, however, a standardized unit of electrical charge did not exist. Coulomb solved this using geometric symmetry. He took a metallic sphere with an unknown charge, let's call it Q, and placed it in direct contact with an identical, uncharged sphere. The conductive nature of the metal distributes the total charge equally across both surfaces. When separated, each sphere is left carrying exactly half the original charge, or Q/2. By repeating this process, Coulomb could reliably produce predictable fractional ratios of charge, like Q/4 or Q/8. With a method to control the charge ratios, he then systematically varied the physical distance between specific pairs of charged spheres, measuring the resulting force at each new separation. The data revealed a strict mathematical pattern. The electrostatic force dropped inversely with the square of the distance between the spheres, and it scaled directly with the product of the magnitudes of the two charges. By leveraging the symmetry of identical spheres, Coulomb successfully deduced the core scalar proportionality of electrostatics without ever needing an absolute unit of measurement. However, a proportional relationship is only a blueprint. To use it as a solvable equation in applied physics, it requires a constant of proportionality to tie the variables together. In the SI system, we insert the constant K. Its value is approximately 9 × 10 to the 9th power, measured in Newton square meters per square Coulomb. This specific value for K actually defines the modern unit of charge itself. 1 Coulomb is defined as the amount of charge that, when placed exactly 1 meter away from an identical charge, generates exactly 9 × 10 to the 9th newtons of force. For deeper theoretical work, the constant K is expanded into its full form, 1/4 pi times epsilon naught. That symbol, epsilon naught, represents the permittivity of free space. It is a fundamental physical constant, 8.854 times 10 to the -12th, that quantifies exactly how much resistance a vacuum offers to the formation of an electric field. This specific formulation is strictly calibrated for a perfect vacuum. If the interacting charges are placed inside a physical medium, like water or glass, the constituent atoms of that material will react, altering the field and requiring a different permittivity value. So far, we have only calculated the magnitude of the force, but in Newtonian mechanics, a scalar magnitude is incomplete. Force is a vector. It requires a specific spatial direction to be physically meaningful. To formalize Coulomb's law, we place the interacting charges within a three-dimensional coordinate system. Let's designate an origin point, O, and plot two distinct charges, Q1 and Q2. We first define their exact locations in space using position vectors, labeled R1 and R2, which trace the precise distance and direction from the origin out to each charge. Next, we need the direct line of force acting between them. We draw a displacement vector, denoted as r21, which points strictly from q1 over to q2. To assign this direction to our equation, without arbitrarily multiplying the actual force, we extract the unit vector, r21. This vector points perfectly along the path from q1 to q2, but has a mathematical magnitude of exactly 1. By multiplying our original scalar magnitude by this unit vector, we arrive at the finalized vector formulation of Coulomb's law. We now have an equation that maps both the immense strength and the exact trajectory of the electrostatic force. If we calculate the reverse interaction, the force that Q2 exerts back on Q1, the displacement vector simply reverses direction, flipping the sign of the unit vector and producing an equal but mathematically negative force. Through this vector formalization, Coulomb's law elegantly demonstrates that electrical interactions are not one-way streets. They inherently embed and obey Newton's third law of equal and opposite reactions. Viewed alongside Newton's law of gravitation, the structural parallels are striking. Both calculate force from two inherent properties, decaying by the exact inverse square geometry. To compare their strengths, we calculate the forces between a stationary proton and electron separated by 1 angstrom. If we plug the known masses of these particles into Newton's equation, the resulting gravitational attraction is on the order of 10 to the negative 47 newtons, a nearly undetectable figure. Plugging the charges into Coulomb's law yields an electrostatic force of roughly 10 to the negative 8th newtons. Dividing the two yields a stark ratio. The electrical force is 2.4 times 10 to the 39th power stronger than their gravitational pull. This presents a physical paradox. If the electrostatic force overpowers gravity by 39 orders of magnitude, why isn't it the force dictating the orbits of planets and the structure of galaxies? The answer lies in the nature of the variables themselves. Mass only has one sign. It only attracts, meaning gravitational forces endlessly accumulate as objects get larger. Electric charge, however, is bipolar. Because positive and negative charges exist in roughly equal numbers, their forces continually cancel each other out on a macro scale. This macroscopic neutrality allows a remarkably weak force like gravity to quietly dominate the cosmos. But deep within the bounds of the atom, where individual charges operate uncancelled, Coulomb's staggering mathematics stands alone as the true architect of matter.